Hello friends, welcome to lecture series on essential mathematics for machine learning. Now in this lecture we will see the concepts of duality which we will use in soft margin or hard margin classifiers. The concept of duality is important to find out Lagrange function, to find out the dual of a given problem, so that it will be the problem will become computationally easy to solve. So, what do you mean by duality and how can you find out dual of a general nonlinear problem? So, first it is some introduction. So, duality is used in mathematical programming for many theoretical and computational developments in diverse fields including operation research, management science and economics. The duality principle, what a duality principle is? The duality principle connects two programs, one the primal which is the constraint minimization or maximization problem, and the other is called the dual for which is a constraint maximization or minimization such that the existence of optimal solution to one of them ensures an optimal solution of the other and the optimal values of the two are. So, the main important concept behind duality is that we have two problems, problem 1, problem 2. It connect the two problem in such a way that if you are having the optimal solution of the one problem, say 1, if you have the optimal solution of the problem 1, then it will ensure the optimal solution of the other problem 2 also, and the objective value of both the problems are equal. So, that is the main concept of duality principle. Now, why duality? So, results developed in duality theory have helped develop various numerical algorithms for solving certain optimization problems. So, it is required in developing various numerical optimization algorithms. So, now the question is how can we write the dual of a given nonlinear optimization problem? So, suppose we have this nonlinear optimization problem, minimization of a function f x subject to g I x less than or equal to 0, I from 1 to m. So, there are m number of constraints and we have a single objective f which is to be minimized. So, this problem we are calling as problem P. So, where this function f is from Rn to R, that means there are n number of unknowns, j are the function from Rn to R for all I. Now, to find out the dual of this problem P, let us first write the Lagrange function of this problem. How we define a Lagrange function? So, Lagrange function is basically function of two parameters x and lambda. X is in Rn and lambda is in Rm. So, lambda are called Lagrange multiplier corresponding to the constraints. How many constraints we are having in this problem P? We are having m number of constraints. So, corresponding we will be having m number of Lagrange multipliers in the Lagrange function. So, the Lagrange function is a function of two unknowns x and lambda which may be defined as the objective function. The objective function is f x here, you see objective function comes here, and the sum of lambda I g I is from 1 to m because there are m number of constraints. So, this lambda 1, lambda 2, lambda 3 up to lambda n, these are called Lagrange multipliers. So, we can also write this problem as f x plus lambda transpose g x. Lambda transpose, see lambda is basically lambda 1, lambda 2 up to lambda m, and g is basically g 1, g 2 up to g m. So, when we multiply these two, then we get g 1 lambda 1 g 1 plus lambda 2 g 2 and so on up to lambda m g m. So, in this way we can write the Lagrange of a given nonlinear programming problem. Now, how can we write a dual of this problem? So, dual may be defined as, the dual of this problem P is given as, we write maximizing of Lagrange function subject to gradient with respect to x of this Lagrange equal to 0, lambda greater than or equal to 0. So, this is how we can define Lagrange, we can define the dual of this problem P. Okay. Now, this dual, this problem can be rewritten as, see what is the Lagrange function? Lagrange function we have already seen, the Lagrange function is basically f x plus summation I from 1 to m lambda I g I. Okay. So, this is Lagrange, this Lagrange will come here, maximization of this subject to Now, the gradient of this function, this Lagrange respect to x. So, gradient of this respect to x will come here, the gradient of this respect to x will come here equal to 0 and lambda I greater than or equal to 0 for all I. So, this is how we can write the dual of this problem P, and this dual is also called Wolf's dual. Okay. So, if we are calling two problem as a, if one problem the first problem is called primal problem and the second problem is called the dual problem. Now, there is some relation between these two, as I already told you that the optimality condition, optimality of one of the problem guarantees the optimality of the other problem and vice versa. So, there are some relations between these two and these are called duality relations. There are certain duality theorems, you see. So, what are those results? Let us first try to understand those results. So, first is if f and gi for all I are convex differentiable functions in this problem. See, in this problem P, if this f and all gi's are convex, then this problem is called convex programming problem, and now we denote this problem as CP. Okay, the problem P we are calling as CP. So, the first result is, which we are calling as weak duality result, states that if x is a feasible solution of CP and u lambda is feasible for problem D, which is a dual of this problem P of this problem CP, then this inequality always hold. This inequality means the minimum value of the objective function of the primal problem P or CP is always greater than or equal to the maximum value of the objective function, the value of the objective function of the problem D. So, how we got this result? So, let us try to understand. So, we are having two problems here. So, what is our primal problem? The primal problem is minimization of f x subject to g j x less than or equal to 0, j from 1 to m. And this problem, if f and g j's are convex for all j, we are calling as CP. And the problem D, which is a dual of this problem CP, is given by maximization of Lagrange function, which is f x plus summation j from 1 to m lambda j g j x subject to the gradient of this should be 0, that means gradient of f x plus summation j from 1 to m lambda j gradient of g j x equal to 0 and lambda j greater than or equal to 0 for all j. So, this problem is D and this problem is CP. So, what is weak duality result? Weak duality result states that if x is any feasible point of the problem CP and u lambda is any feasible point of the problem D, then f x is always greater than or equal to f u plus lambda transpose g u. So, now we have to prove this. So, it is given to us that f is convex and g j for all j's are convex, x is feasible for this problem and u lambda is feasible for this problem D. So, let us try to prove this result. So, since by the convexity of f at u we have f x minus f u is greater than or equal to x minus u transpose gradient of f u. This is by the convexity of f, because f is a differentiable convex functions, hence this result will hold, that we have already discussed in our previous lectures. Now, since u is feasible for this problem D, so you multiply both sides by x minus u transpose. So, that means this will be equal to minus x minus u whole transpose summation I from 1 to m lambda j gradient of g u. Okay. This is because you see u lambda is feasible for this problem D. So, you multiply both sides by x minus u transpose. So, this quantity will be equal to the negative of x minus u whole transpose summation lambda j gradient g j u. Now, again, so say this inequality as inequality 1. So, again by the convexity of g j at u, we get g j x minus g j u is greater than or equal to x minus u whole transpose gradient of g j u. So, multiply by lambda j both sides of the above constraint of the above inequality and sum up all the m inequations, inequalities we get. So, now what we will obtain? Summation lambda, okay, lambda j, it is lambda j g j x summation over j minus summation over j lambda j g j u is greater than or equal to minus x minus u whole transpose summation j lambda j gradient of g j u. This is, suppose this is in equation 2. Now, you can use this in equation because this side is less than or equal to this side. Oh, this is positive, this is not negative, this is positive. So, now you from 1 and 2, see this side is less than or equal to this side, okay, and the negative of this side is greater than or equal to this side. So, using from 1 and 2, what we obtain? From 1 and 2 we get, here we obtain this, from this side it is f x minus f u is greater than or equal to, so you multiply both sides with minus 1. So, this factor will come before, okay. X is feasible for this problem. So, g j x will be less than or equal to 0 for every j, okay. So, negative of g j will be greater than or equal to 0 for all j and lambda j's are non-negative. So, from this we will obtain that this quantity with negative sign is greater than or equal to 0. So, that means it is greater than or equal to g j lambda j g j u plus 0, okay, because this is less than or equal to 0 for every j and lambda j's are non-negative. So, when you multiply and sum it up for all j, so this quantity will be less than or equal to 0, with negative it will be greater than or equal to 0. So, what we obtain from here now, it is f x is greater than or equal to f u plus summation over j lambda j g j u. So, hence we got the result. So, this is our weak duality result. So, basically weak duality result is important to find out the bound of the problem, either primal problem or the dual problem. If there is any u or lambda which is feasible for the problem D, then we can easily say that this value will be finite for that u and lambda, and f x will always be greater than or equal to that value. So, that will be helpful in finding out the bound of a given problem, or the primal problem or the dual problem. Similarly, if you know x as a feasible problem for the problem C p, then you know this value, some finite value, then we can say that the objective function of a dual problem will always be less than or equal to that value. So, this is helpful in finding out the bounds of the primal problem or the dual problem. Now, the next result from the weak duality result, that if x bar is a feasible point of C p and u bar lambda bar is feasible for D, and suppose the value of the objective function of the primal at x bar and the value of the dual problem at u bar lambda bar both are equal, both coincides, then x bar is the optimal solution for C p and u bar lambda bar will be the optimal solution for problem. So, the proof is again very easy to obtain. See here what is given to us. It is given to us that f x bar is equal to f u bar plus summation over j lambda j bar g j x u bar. So, it is given to us, and we have to show that x bar and u bar lambda bar are nothing but the optimal solutions of the primal or dual problems. So, if you want to show that x bar is an optimal solution of the dual problem, then we need to show that f x bar will be less than equal to f y for any feasible y to problem C p. So, let us try to prove this result. Proof: let y be any feasible point of the problem C p. Okay. So, we need to show that f x bar is less than or equals to f y. Okay. This we need to show. So, now by the weak duality result, we have f y is greater than or equals to f u bar plus summation over j lambda j bar g j u bar. Since y is feasible point for the any feasible point of the primal problem, and u bar lambda bar is also a feasible point of the problem D, then by the weak duality result this inequality will hold. Okay. And this quantity is nothing but is equal to f x bar. So, it is equal to f x bar. So, this implies f x bar is always less than or equals to f y, and hence we can say that x bar is nothing but the optimal solution of the primal problem, because this value is always less than or equal to f y for any feasible y. So, that means x bar is the optimal solution of the primal problem. And similarly, if you want to show that u bar lambda bar is an optimal solution of dual problem, then so this implies x bar is the optimal solution of the C p. Now, let u lambda be any feasible point of the problem D. Okay. Now, we have to show that u bar lambda bar is an optimal solution. That means, so we need to show that f u bar plus summation over j lambda j bar g j u bar is greater than equal to f u plus summation over j lambda j g j u, because it is a maximization type problem. So, again this is easy, because by the weak duality results what we have, we have f x bar is greater than equal to f u plus summation over j lambda j g j u, because x bar is the feasible point of the primal problem and u lambda is the feasible point of the dual problem. So, this implies, since this is equal to, because this is equal to this, so we can replace this by this. So, this implies f u bar plus summation over j lambda j g j u bar is greater than equals to f u plus summation over j lambda j g j u bar g j u. So, this implies u bar lambda bar is the optimal solution of D. So, hence we have proved the result. So, in this way we can say that if the optimum values of the primal and dual are equal, then the points where they are equal are nothing but the optimal solutions of the respective problems. So, next is strong duality result, which states that if x bar is a feasible point of CP and the basic constraint qualification hold at x bar, then there exists lambda bar such that x bar lambda bar is optimal to the problem D. Further, the optimal values of the two objectives coincide. So, basically weak duality result is helpful in finding the bounds of the primal or the dual problems. Okay. And the strong duality result guarantees the optimal solution of the one problem if we have the optimal solution of the primal problem. If we have the optimal solution of the primal problem, then there exists an optimal solution of the dual problem and the value of the objective values of both are equal. Okay. So, now let us try to find that how we can write a dual of a QPP, quadratic programming problem. So, this is a quadratic programming problem. So, how we can write a dual? We already know that this is a QPP because objective function is quadratic in nature and all constraints are linear. So, here A is a m cross n matrix, C and x belongs to Rn, B belongs to Rm and Q is a n cross n symmetric positive semi definite matrix. So, again to write a dual we can first write the Lagrange of this function. So, what is the problem we are having? Problem is minimizing C transpose x plus 1 by 2 x transpose q x subject to a x less than equal to b and x greater than equal to 0. Now, this constraint can be rewritten as a x minus b less than equal to 0 and this constraint can be written as minus x less than equal to 0. Let the Lagrange multipliers corresponding to these constraints are u and let the Lagrange multiplier corresponding to these constraints are v. So, L, which is now a function of x, u and v, can be written as, first is the objective function. Objective function is what? C transpose x plus 1 by 2 x transpose q x, okay, plus now it is u transpose a x minus b, there is u transpose g x. It is u transpose a x minus b, g x is this and this collectively we are calling as g x and this is plus v transpose minus x. So, this is the Lagrange function of this problem QP, this problem is QP. Now, how can we write a dual of this problem? So, the dual of this problem will be D, yeah, QD will be, now it is maximization of L x u subject to gradient with respect to x of L will be 0 and u greater than equal to 0 and v greater than equal to 0. As we have already discussed, the dual of a given NLP, given nonlinear problem will be nothing but the Wolf's dual is nothing but maximizing of the Lagrange function subject to gradient with respect to x of L is 0 and the Lagrange multipliers must be non-negative. So, now let us rewrite this problem. So, what will be QD now? It will be maximization of 1 by 2 C transpose x, oh it is not 1 by 2, it is, see here, it is C transpose x. So, it will be C transpose x plus 1 by 2 x transpose q x plus u transpose a x minus b minus v transpose x, subject to what are the conditions. So, you can verify from here, subject to gradient with respect to x. So, what will be gradient with respect to x? You differentiate this function with respect to x. So, it will be c plus q x, because q is a symmetric matrix, otherwise it will be q transpose x, but here q is a symmetric matrix. So, q transpose will be q plus it will be A transpose u and minus v equal to 0, v I equal to 0. Okay. And this u is non-negative and v is non-negative. Okay. Now, this can be rewritten as, now if you see, if you multiply this equation by by x transpose, so what we will obtain? So, it will be x transpose c plus x transpose q x plus x transpose A transpose u minus x transpose v equal to 0, and x and u and v non-negative. Okay. So, I am trying to like rewrite these equations, this problem. So, basically dual is this, but I am trying to write this problem in a simplified way. So, I can replace this quantity, this is x transpose v, which is same as x transpose v whole transpose, because this is a scalar quantity. So, this is equal to v transpose x. So, I can replace v transpose x from this equation to this. So, if I replace this, from here to this equation, what I will obtain finally. So, finally, I will obtain, now you can see from here. So, this is the dual which we are already obtained. So, now you can replace v from this equation to this. Okay. So, if I replace this, finally after simplification of this simple equation, I will obtain this. Now, this is equal to v. So, I can write v as greater than equal to 0. So, it will be greater than equal to 0. Okay. So, v is eliminated from the entire expression. So, now I can say that this is also the dual of this problem QP, Okay. So, let us take a problem now. Suppose you are having this QPP and you want to write a dual of this QPP. So, how can you write? So, what is the QPP now? It is minimization of x1 minus 6 whole square plus x2 minus 4 whole square, 4 and 6, okay. It is 4 here, 6 here, subject to what are the equations? The first equation is 2x1 minus x2 less than equal to 6, and x1 minus x2 less than equal to 2, and x1 x2 non-negative. So, this is the primal problem. So, what will be the dual of this problem? We have already seen the dual will be nothing but it will be x1 minus 4 whole square plus, or if you want to eliminate u, then that will be nothing but, so you have to, otherwise you have to transform. So, anyway you can write in that way only, x2 minus 6 whole square plus, so let the Lagrange multiplier corresponding to this is u1, for this is u2, for this is a v1 and v2. So, u1 2x minus x2 minus 6 plus u2 times x1 minus x2 minus 2 minus v1 x1 minus v2 x2. Okay. Subject to, now you take the gradient of this problem. The gradient will be 2 x1 minus 4, first with respect to x1, 2 x1 minus 4, it is plus 2 u1 plus u2 minus v1 equal to 0, and it is 2 x2 minus 6 minus u1 minus u2 minus v2 equal to 0. Okay. u1 u2 v1 v2 non-negative. Now, so this is a dual of this problem, this is a dual. Okay. Now, at this point 0.8 4.4. So, if you are taking x1 as 0.8 and x2 as 4.4. So, it is satisfying all the constraints, this point is satisfying the constraint, and the objective value of this problem is, suppose this objective value is f and this is suppose g, the objective value coming out to be 12.8. Okay. Now, if we take this problem, then here we take x1 as 0.8, x2 as 4.4, okay, and u1 as 1.6, v1 v2 u1 u2 both all are 0. So, this is basically, so lambda 1 here given as 3.2. So, it is 3.2. Now, if you take this point satisfying both the dual constraint, all the dual constraints in fact, and the objective value at this point is also the same as f, is also the z is also at this point is 12.8. You can verify very easy you can verify, because when x1 is 0.8 and x2 is 4.4. So, this is 0. So, this is 0, u2 v1 v2 are already 0. So, this whole quantity is 0. So, we will left with only these two terms which are same as the which is same as the two terms of f. So, this is nothing but the same objective value. So, hence we can say that since the value of the objective function at these 2 points coincide, so these are nothing but the optimal solutions of the this problem and this problem respectively. Okay. So, in this way, if you want to write out a dual of a given NLP, here for illustration I have taken a quadratic programming problem. In general, if you are having any nonlinear problem which is a convex programming problem, then you can write the Wolframe's dual in this manner. You have a given nonlinear problem, minimization type subject to GJX less than or equal to 0. You can write a dual as the maximization of the Lagrange function subject to gradient of Lagrange respect to x equal to 0 and all Lagrange multipliers greater than or equal to 0. So, that is a general format of writing a dual of a given nonlinear programming problem. So, thank you very much.